In this video, we're gonna have a short review on sets, and then later on we'll talk about the set of real numbers, okay? So a set simply is a collection of any kind of things. It can be a collection of numbers, letters, objects, anything, okay? But more specifically, a set is a well-defined collection of distinct objects. By well-defined, it means that there is a certain rule that allows us to determine whether a given object qualifies to be a member of a particular set. Okay, in other words, these objects must share the same property or properties. All right, and we call these objects as elements or members of a set. Okay, for example, so we have here set of all small vowel letters. All right, let's denote this set as capital V. Okay, and so we say that V consists of the letters A, E, I, O, and U. All right, as you can see, we use braces or curly brackets to enclose the elements of the set. And this particular method of describing a set is what we call the roster method. Okay, so in this method, we just list all of the elements that satisfy the given rule or property. All right, and then later on, we'll discuss some more methods of describing sets. Okay, then let's have another example. We have here the set of all natural numbers. This is actually a special set, right? It's a subset of real numbers, and it's denoted by n here. And it consists of all counting numbers. So 1, 2, 3, 4, so on and so forth. The ellipsis here means that this continues to infinity, or this pattern continues infinitely. All right. All right. Speaking of real numbers, these are numbers that we normally encounter in our daily lives, right? We use them to quantify many real world quantities like your height, your weight, your body temperature at any given time, your calculus grade, so on and so forth. And we use them practically in any sort of calculations, okay? So with this, we can say that real numbers are numbers that are measurable. And when we say measurable, we mean that these numbers can be mapped or plotted on a number line like this one. Okay, so 0 here is referred to as the origin. Okay, and the numbers to the right of 0 are the positive real numbers, and the numbers to the left of 0, these are the negative real numbers, right? So again, any number that can be plotted on a number line is a real number. Okay, so let's have some examples. Say -4, right? We can clearly see it on the number line. It's this point here. So it's a real number because it can be plotted on the number line. Now, how about 1/2 or 0.5? This number is the midpoint between 0 and 1. So it's this point here, right? Therefore, it's also a real number. Now, let's say square root of 2. Okay. Now, before we locate or pinpoint its location on the number line, let's look at this triangle here. Okay. So let's say that this length here is measured to be 1 unit. Okay. And let's say the length of the base is also 1 unit. Okay. Now, how do we determine the length of the longest side or the hypotenuse? So according to the Pythagorean theorem, the hypotenuse or the longest side or the length of the longest side is square root the sum of the squares of the other two sides. Okay, so that would be square root of 1 squared plus 1 squared, or square root of 2, right? And since this triangle exists, then square root of 2 also exists, right? Therefore, it's a real number. So it's roughly this point here. Okay. Now, how about the constant pi? which is approximately 3.14159. Okay. Now, pi is the ratio between the circumference of any circle and its diameter, right? And since circles exist, or since circles are real, then pi is also real. And so pi is a real number, right? And we can find it somewhere here at this point. So it's approximately, again, it's approximately 3.14159. All right. So now let's look at some subsets of real numbers. Starting with the natural numbers, right? This consists of all counting numbers, 1, 2, 3, 4, so on and so forth. And then if we include 0, then we have the set of whole numbers. Okay. So far we have 0 and natural numbers or counting numbers, which are essentially positive numbers. Okay. And if we include negative numbers, then we have the set of integers. Okay. Now, we also have to account for all the other numbers in between these integers. Okay. So these are the fractions and some other numbers that cannot be expressed as fractions. So fractions, for example, we have 1/2, 17/40, 8/9, and some other numbers, again, that cannot be expressed as fractions, like square root of 2, square root of 19, and the constants pi, and the Euler's number e. Okay? Now, this group on the left side, these are numbers that can be expressed as fractions, as I've said earlier, right? In other words, these are numbers that can be expressed as a ratio of two integers. Okay, so if you look at these examples of fractions here, we have 1/2, 17/40, 8/9. Basically, the numerator and the denominator are integers. So we have a ratio between two integers. Okay, and then the integers themselves can also be expressed as a ratio of some other integers, like for example 3. So for example, let's consider 3. Okay, 3 can be expressed as 3/1, which is a ratio between two integers, right? It can also be expressed as 6/2, which is still a ratio between two integers. Or we can also write this as 12/4, which is again still a ratio between two integers. All right. So again, this group here consists of real numbers that can be expressed as a ratio of two integers. Hence, we call them rational numbers. Okay. And then all the other numbers, or all the other real numbers that cannot be expressed as a ratio of two integers, like these numbers on the right hand side, we call them irrational numbers. Okay. So let's talk more about rational and irrational numbers. Let's focus first on rational numbers. Okay, again, these are numbers that can be expressed as a ratio of two integers. Okay, so it includes all integers and fractions. For example, let's look at 6. 6 can be expressed as the ratio between 6 and 1, where 6 and 1 are integers, right? We can also express 6 as ratio between 12 and 2, or 12 divided by 2, where 12 and 2 are integers. Okay, therefore this number and all the other integers, they satisfy the condition that we have here for rational numbers, or the property for rational numbers, right? Meaning we can have any integer divided by any integer, like the fractions we had earlier, 1/2, 17/40, 8/9, and 50/111, for example. Okay, as long as the denominator is not 0, like for instance 8 divided by 0. This is an undefined number or undefined value. Okay, so it's not a real number. Now, we can also express these fractions as decimals, right? So 1/2 is 0.5, 17/40 is 0.425, 8/9 is 0.8888, so on and so forth. So we can just simply say 0.8, repeating, right? And then 50/111 is 0.450, 450, 450, so on and so forth. Or we can just simply say it's 0.450, repeating. Okay, the first two are what we call terminating decimals, okay, because there is a stopping point, if you will, right? Meaning the numbers stop at a point, okay, and they do not go on and on, or they do not continue infinitely like the other two decimal numbers. Like, so these two, on the other hand, 8/9 and 50/11, their equivalent decimals are what we call non-terminating repeating decimals, okay, because they follow a certain pattern. In this case, numbers are repeated as they go on and on, as they continue to infinity. Okay, so 0.8 is repeated, I mean 8 in this case is repeated, and then for 50/111, 450 are repeated as it continues infinitely. So we say 0.8 repeating and 0.450 repeating. Okay, and then for the irrational numbers, again, these are numbers that cannot be expressed as a ratio of two integers. Okay, so we have square root of 2, square root of 15, the constants pi, and the Euler's number e, right? So if we convert them to decimal numbers, square root of 2 is 1.41421, so on and so forth. Square root of 15 is 3.87298, so on and so forth. And then pi, so these are the first few decimal numbers for pi, 3.14159, so on and so forth, right? And then Euler's number is equivalent to, or approximately, 2.71828, so on and so forth. Okay, so their decimal equivalents, they continue infinitely. That's why we can also call them non-terminating decimals. However, as they continue infinitely, they do not follow a certain pattern, right? So we call them non-terminating, non-repeating decimals. Okay, so these are the set of rational numbers and irrational numbers. Okay, again, we have the set of rational and irrational numbers, and all of these numbers together make up the set of all real numbers, right?